Hello everyone, and welcome to your continuation of the respiratory system. So we ended up right before discussing compliance. And what compliance is, it's going to be the measure of ease with which our lungs and thorax are going to expand. And this really is determined by the amount of surface tension and elasticity of our chest wall and lung that is going to determine the amount of our compliance. The greater compliance we have, the easier it's going to be to change the pressure and allow our thoracic cavity to expand. If we have a lower than normal compliance, then our lungs and thorax are going to have a harder time expanding. So our normal person is going to have a compliance of 0.18 liters per millimeter mercury. Now what that means is for every 1 millimeter mercury of change in our intra-alveolar pressure, the volume is changing by 0.18 liters. So when we do have these situations where we have a lower compliance than what's ideal, it's usually caused by some type of respiratory disorder or anatomical abnormality that's going to cause an increase in resistance to the airflow that's associated with either a decrease in the size of the lumen of our bronchioles, like in asthma. So we have increased resistance of airflow here caused by an airway obstruction, asthma, bronchitis, or lung cancer. Or it could be a decrease in compliance. So for instance, in pulmonary fibrosis, where we get a deposit of more of these inelastic fibers within our lung. And I just want to mention that not usually, but sometimes we have more of a combined syndrome with pulmonary fibrosis and emphysema, where we are going to see a characterization of dyspnea or painful breathing, upper lobe emphysema, where more of the alveoli are going to kind of not have as much surface tension, not surface tension, surface area. So it's going to be a little bit lower ability to provide gas exchange there. We have lower lobe fibrosis, where we have more of those inelastic fibers and just general abnormalities of gas exchange taking place here. We also will have pulmonary edema, which in this case we're going to have more collapse of the alveoli. So obviously when they're collapsed, we don't have good gas exchange. And this collapse of the alveoli can happen in our respiratory distress syndrome that we discussed in class. And then we have our deformities of the thoracic wall, so that would be more of an anatomic abnormality. Remember that kyphosis was that abnormal curvature of the thoracic vertebrae, more of an exaggerated curvature, let's say, and scoliosis was more of a lateral curvature of the spine, which is abnormal. Also, I wanted to put this chart in here just to show you that we have greater resistance in our medium-sized bronchi, so like our secondary bronchi, let's say. And then from there on out, as we branch into our smaller terminal bronchioles and get into our respiratory zone, so this would be like our respiratory bronchi and our alveolar ducts and so forth, but we are going to see that there's going to be less resistance as we get into these smaller bronchioles and alveolar ducts. So next we're going to talk about the measurement of lung function, and we are going to, in your Learn Smart lab, perform a spirometry, which is a test which measures the volumes of the air that move into and out of the respiratory system. So remember that is due Sunday for you guys. And in order to do this, we use a spirometer, which is the device that measures these volumes. So let's talk about these volumes. So we have a tidal volume, which is just going to be that normal air that you're moving in and out of your lungs. So as you're sitting here watching the screencast, this is your tidal volume. It's about 500 milliliters, but this is going to vary by age, sex, height, and fitness just like all these other volumes, they're going to vary because each of these factors, gender, age, body size, physical condition, is going to change your respiratory volumes and your capacity. So, for example, we're going to talk about vital capacity soon, but this is going to be about 20 to 25% less than that of adult males for the females. So let's continue on here. We have our functional residual capacity, and this is going to be the volume of air that is remaining in our lungs at the end of normal expiration. So if you just breathe out normally, that amount that's still left in your lungs is your functional residual capacity. Next, we have your inspiratory reserve volume, and that will be the amount of air that can be forcefully inhaled after normal inspiration. So just breathe in normal, and then continue to breathe in as much as you can to pull in all of that air, and this is going to be about 3,000 milliliters at rest. Next, we have your expiratory reserve volume, and that is going to be the amount of air that can be forcefully exhaled after normal expiration. So let it out, and then you can kind of contract your abdominal muscles and those internal intercostal muscles, just pushing all of that air out of your lungs as much as possible. And that is going to be 100 milliliters at rest. Next, we have your residual volume, and this is air that we cannot take out of our lungs. It's the volume of air that's remaining in our lungs after the maximum amount of expiration. So if you guys were kind of demonstrating this while watching the screencast, you let all of that air out of your lungs as much as possible, contracting your abdominal muscles, your chest muscles to push that air out. What's left in there is residual volume. And so we're glad this residual volume stays in our lungs, because if it was not there, our lung would collapse. And next we have your vital capacity, and this is the maximum amount of air that we can move into our respiratory system and out in one single cycle. So we're kind of adding all of these other volumes or capacities together. We have your inspiratory capacity, inspiratory reserve volume, expiratory reserve volume, and tidal volume, all added together to get this vital capacity. So here's the graph that you have in your book where they break it down. You could see your tidal volume is here. That's your normal breathing. We had your expiratory reserve volume, which is the maximum amount of expiration that you can do. That residual volume that is left in your lungs after you push all the air out. And then we have your inspiratory reserve volume, which is all the air that you can breathe in after normal normal inspiration here. And then the rest of these capacities are all volumes that we can add these volumes together for. So inspiratory capacity is that normal breathing volume added to your inspiratory reserve volume. So it's all the air that you can breathe in. Vital capacity is all the air that you can move in and out of your lungs. And then total lung capacity is all of the volume, including that residual volume that's left in your lungs after complete expiration, all added up to get total lung capacity, which is usually around 5,800 milliliters. So that brings us to minute ventilation and alveolar ventilation. So what minute ventilation is the total air that is moved into and out of our respiratory system each minute. And we can calculate this by taking our tidal volume and multiplying it by our respiratory rate. So like a normal respiratory rate would be about 12 breaths per minute, and our normal tidal volume we just saw was right around 500 milliliters. So if we do the math, we are going to get about 6,000 milliliters per minute. So that's going to be normal gas exchange. Oh, excuse me, that's going to be a normal minute ventilation. What I wanted to say is that this doesn't necessarily mean that we're measuring the amount of air available for gas exchange. But it's clinically important because it's going to indicate the amount of carbon dioxide levels that we have. And we're going to discuss carbon dioxide levels in the future slides here. So I mentioned respiratory rate here in our minute ventilation. This is the number of breaths that we can take per minute. So you can have a timer in front of you and sit there and just normally breathe, and you can count your breaths, and that's your respiratory rate. Now, to discuss the anatomical dead space and physiological dead space, I want to mention alveolar ventilation first. And this is going to be the volume of air available for gas exchange per minute. So this is similar to minute ventilation, but like we said, it has to do more with gas exchange. So it's a little bit more accurate as far as that volume. And in order to do this, we need to take into account our dead space. So our anatomical dead space is going to be all of the area where gas exchange is not going to take place. So areas like our nasal cavity, pharynx, larynx, trachea, bronchi, bronchioles, and terminal bronchioles. We know at the level of our respiratory bronchioles, alveolar ducts, and alveoli is where gas exchange is going to occur. Now we also have physiological dead space, and this is any area where gas exchange is not taking place that is due to damaged alveoli or for whatever reason not allowing gas exchange to take place normally. So in a healthy person, the anatomical dead space and physiological dead space is pretty much even, because hopefully all of their alveoli is functioning correctly. But with people who have physiological dead space, so they're suffering from emphysema due to degeneration of their alveolar walls, or have small alveoli that are combining to form larger alveoli, so we're reducing the amount of surface area there. These people are going to have a greater amount of physiological dead space, so we need to take that into account. So by considering these two areas of dead space, we subtract it from the other volume of air that we're able to measure, and we get our alveolar ventilation, or the amount of gas exchange that can take place per minute. So in this image, it's just depicting for you this anatomical dead space where we have more of our bronchioles or bronchi, and in white we're seeing the alveoli that are working correctly. And here we see our physiological dead space, or it's also known as an alveolar dead space, where maybe we're not getting blood supply to this area, or half of the alveoli is really functioning correctly, so it's been compromised here and not working properly. Okay, so now we have our physical principles of gas exchange. So here we're talking about our diffusion of gases through our respiratory membrane, and it's going to depend on 4 major factors. We have our membrane thickness, so based on the amount of thickness of our membrane, our respiratory membrane, remember this is including the alveolar wall, that interstitial, first we have our surfactant, then we have your alveolar wall, then you have your interstitial space, and then you have your capillary layer, which is your endothelial layer. So remember, all of that is your respiratory membrane. So if we have a very thick respiratory membrane, we're going to have a lower amount of diffusion taking place there. Our increased respiratory membrane thickness is going to be an accumulation of fluid in the alveoli, and this is pulmonary edema. So in that case, that's what's causing the membrane thickness to be larger. So we're getting a decrease in the diffusion rate. Our second factor is the diffusion coefficient of gas. So this is the measure, it's like a volume of measure of how easily the gas is diffusing through a liquid or a tissue. And what's interesting is that our carbon dioxide is 20 times more diffusible than oxygen. So what this means is carbon dioxide is going to diffuse through the respiratory membrane about 20 times more readily than oxygen does. And then I want you to, let me get this to work, I want you to just cross off this here because we're going to talk about it down below. Not good editing on my part. Okay, so now on to our surface area. So our surface area is the amount of space we have for gas exchange to take place on our respiratory membrane. And in healthy adults, we are going to have about 70 meters squared amount of surface area within the lungs. So people that have diseases like emphysema and lung cancer, they're going to have reduced surface area. And because they have reduced surface area, they have less space or less of an area for gas exchange to take place. And this is due to maybe you have surgical removal of lung tissue if you have cancer, or you have destruction of lung tissue due to cancer, or in emphysema, we have degeneration of those alveolar walls, or sometimes our smaller alveoli become larger alveoli, and so that's reducing the amount of surface area that we have there. And number 4, we have partial pressure differences. So our gas is always going to move from a higher area of partial pressure to a lower partial pressure. And normally, partial pressure of our oxygen is going to be higher in our alveoli than it is in blood. So it's going to want to move from the alveoli over into our capillaries. And the opposite is true for our carbon dioxide. So we're going to have a higher partial pressure of carbon dioxide in our blood that will want to move into our alveoli. And that's great because we can move it into the alveoli and breathe it on out. Okay, so next we have our oxygen and carbon dioxide transport in our blood. I cut a little bit out of this section because we talked about it in our blood lecture in chapter 19. But for our oxygen, we have oxygen moving from our alveoli into our blood. Remember, this is called external respiration, and our blood is almost completely saturated with oxygen when it leaves the capillary. As we're moving through that, through our circulatory system, our partial pressure of oxygen is going to decrease in our blood because it starts mixing with deoxygenated blood. And our oxygen is moving from our capillaries now into our tissues. And remember that this is called internal respiration. Now for carbon dioxide, we're going to move from our tissues into our tissue capillaries. So it can be carried back to our heart, and we're going to move from pulmonary capillaries into our alveoli so it can be so we can breathe it out. So here we can see this all outlined in this figure for gas exchange. So let's start at number 1. We have our partial pressures here. We can see that in our alveoli, we have a partial pressure of 104 for oxygen, and within our blood, we have it at 40. So naturally, our oxygen is going to want to move into the blood capillary here, and then our partial pressure for carbon dioxide is 45 in our blood and 40 within our alveolus. So naturally, it's going to want to move into the alveolus here. So we have this diffusion take place at our venous ends of our pulmonary capillaries, and our partial pressure of oxygen is going to be equal at this level when we expire. So we have 104 here, 104 here, and same with the carbon dioxide, 40 here and 40 here. So as we continue on down, we see that our oxygen levels here are 104. So they're kind of at its highest as we're leaving our lung, but as we're continuing on through, we are draining blood, deoxygenated blood from our veins, draining our bronchi and our bronchioles. So we're still in our lungs, and then we make our way to our pulmonary veins. So by the time we get over here, our oxygen levels are going to drop to 95 because, again, we're mixing with that deoxygenated blood from our bronchi and our bronchioles. So continuing on down, we go through and we get to our tissue capillaries now. And I notice that there's an error here in this image. It's correct in your actual print of your textbook, but it's a mistake in this illustration that they've provided for me. So I want you to get rid of this C in your notes. That's supposed to be partial pressure of oxygen there. Okay, so what's happening here is we have our partial pressure of oxygen here at 95, and in our tissues it's at a 40. So we're going to want to move our oxygen into our tissues and then move our carbon dioxide out from a level of 45 to 40. And then we are going to have everything equaled out here as we are leaving this, this tissue and continue back to the heart where this blood can be reoxygenated and continue throughout the body. So that brings us to this dissociation curve. And this is really going to describe the percentage of our hemoglobin saturated with oxygen at any given partial pressure of oxygen. So when we're looking at this graph here, we are comparing the percentage of oxygen saturation, so the amount of oxygen that is saturating our hemoglobin molecules, compared to our partial pressure of oxygen. So we're going to start at this side of this curve here. So when we have our hemoglobin picking up oxygen from our blood, leaving our lungs, so at that point we were at 104 millimeters, millimeters mercury. So that's our partial pressure of oxygen at that point when we are leaving our lungs, making our way back into the heart. And at this point, our hemoglobin is 98% saturated. So we can see in this image here, they basically have almost all of this represented glass filled up because our hemoglobin is completely saturated with oxygen. Then if we continue through the tissues, remember we start giving some, as we continue through the capillaries, we continue to give off more and more oxygen, reducing our partial pressure of our oxygen. So we can go to as low as 60 millimeters per mercury, 60 millimeters mercury or 40 millimeters mercury, and at this point we are still 75% saturated with hemoglobin. So we're not seeing a huge change here as far as the amount of oxygen that's saturating our hemoglobin, but we are seeing a big change as far as our partial pressure of oxygen. And then we continue on down and we start to lower our partial pressure even more. And at this point, maybe we have a demand on our body that is causing us to use up more oxygen. In this case, they've used exercise. So we know when we exercise, our skeletal muscles are going to request more oxygen if they are going through aerobic respiration. So at this point we are at 15 millimeters mercury and our hemoglobin is 25% saturated because we're taking all that oxygen bonded to our hemoglobin and giving it to our tissues. So what this is showing us is we have more of a steeper slope here as we're continuing on down, and that's because we have a small change in our blood partial pressure of oxygen, but we're going to have a larger change in our hemoglobin saturation here. So that's why we have that steep slope. So the take-home message here is as our tissues use more oxygen, our hemoglobin is going to release more oxygen to those tissues. So we don't see that huge change as we're just normally functioning, giving off that oxygen to our body tissues, but when our body calls upon more oxygen, we're seeing a larger difference here. And so now we're going to talk about the Bohr effect, and this is the effect of pH on our oxygen hemoglobin dissociation curve that we just talked about. So as our pH of our blood is going to decline, so we are having more acidic blood, the amount of our oxygen bound to our hemoglobin at any given partial pressure of oxygen is also going to decline. So we can see that our our curve is going to shift to the right here. So we're following this curve right in here. This occurs because this decrease in pH is going to yield increase in hydrogen that's going to combine with hemoglobin, changing its shape, and oxygen cannot bind to hemoglobin as readily. And I forgot to mention here, I don't have a blurb on it, but if we have a shift and we have low carbon dioxide levels yielding high pH, or more basic, we're going to have a shift to the left here. So that brings me to the Haldane effect. The lower the partial pressure of oxygen and hemoglobin oxygen saturation, the more carbon dioxide that can be carried in blood. So basically, if we have these red blood cells that aren't really combining with oxygen, that means we have more hemoglobin molecules to combine with carbon dioxide. So about 23% of our blood carbon dioxide is transported bound to hemoglobin. And this ability for carbon dioxide to be able to bind to hemoglobin when we have these low oxygen hemoglobin saturation levels is this Haldane effect. And the reverse is true as well. So if we have a lot of hemoglobin oxygen saturation and a high partial pressure of oxygen, that means the less carbon dioxide can be carried in blood. So our reduced hemoglobin is going to buffer our hydrogen ions and form carb-amino hemoglobin more easily. And our process encourages our carbon dioxide to exchange at our tissues and at our lungs. So we're bringing back this Bohr effect here. So at our tissues, as more carbon dioxide is entering our blood, more oxygen is going to dissociate from hemoglobin. And as that oxyhemoglobin releases its oxygen, it's able to carry more carbon dioxide in the form of carb-amino hemoglobin. So we have our effects of carbon dioxide and temperature and the amount of oxygen that can be carried. So if we have an increase in our partial pressure of carbon dioxide, this is going to cause a decrease in pH. So this is when we're bringing back this beautiful formula here. We see we have carbon dioxide combining with water, and we can turn into our carbonic acid through our enzyme carbonic anhydrase, and we are going to be able to ionize this into our hydrogen and bicarbonate ion. When we get an increase in temperature, we are going to decrease the tendency of our oxygen to remain bound to that hemoglobin. So as our metabolism goes up, more oxygen is being released to our tissues. You can see that happening over here. Here's our hemoglobin oxygen that's combined. They separate and oxygen is given to our tissues. So this is the shift in curve that we were discussing earlier. So I'm going to let you take a look at this slide on your own. And here we're going to talk more about carbon dioxide transport. So what we're going to discuss first is our tissue capillaries, and that's what we're seeing here, an exchange between our capillary and our tissues. So as our carbon dioxide is entering our red blood cell, it's reacting with water once again to form our bicarbonate and hydrogen ions. This is going to cause a chloride shift. So that's what you're seeing over here. Our chloride ions are entering our red blood cell and our bicarbonate ions are leaving. So that's the shift that's taking place there in order to get these bicarbonate ions out. What our hydrogen ions are going to do is combine with hemoglobin, and we are lowering the concentration of our bicarbonate ion and our hydrogen ion inside our red blood cell, and that is promoting our conversion of carbon dioxide to our bicarbonate ion. Because as we have less products here, we're going to take those reactants and continue this process. Next, what we have is a view into our pulmonary capillaries. So here's our pulmonary capillary, and this is our alveolus here. So our carbon dioxide is leaving our red blood cell, resulting in formation of additional carbon dioxide from our carbonic acid. So now we're moving more in this direction here. Our bicarbonate ions are going to be exchanged for our chlorine ions, so we're just having the opposite happening here, and our chloride shift out, and we're using this bicarbonate ion to continue to form our carbonic acid into carbon dioxide and water to move that carbon dioxide into our alveolus. So when we have increased plasma carbon dioxide, this is going to decrease our blood pH, and our respiratory system is going to regulate our blood pH by regulating the plasma carbon dioxide levels. So they kind of go hand in hand. This is an image depicting what we just talked about. I left these in because these are the ones that you have in your book. So I'm going to let you walk through this as a review of what we just talked about here on slide 64. So continue at your own pace. And I'm going to end this. This will be part 1, and then we'll start at the regulation of ventilation for part 2.